All right, everyone, welcome. This is it, your final exam review for physics. Today we're going to absolutely nail some of those fundamental topics, the ones that always show up and can seriously make or break your grade. My whole goal here is to get you feeling so confident that you walk into that exam ready for anything. So let's just dive right in.
We've all been there, right? You totally get the physics. You've done all the hard work, but then you lose those easy marks because of some little mistake with significant figures. Ugh. Or what about when you're deep into a problem and you just get that gut feeling that something's gone wrong with your equation? Well, guess what? Today, we are building the exact toolkit to make sure that doesn't happen.
So, here's our game plan for today. We're going to start with the basics, the universal language of science. Then, we'll get our hands dirty with measuring precisely. After that, it's all about mastering the rules of significant figures, and then we'll unleash our secret weapon for checking our work. And of course, we'll wrap it all up with some real final exam practice. Sound good? Let's go.
Okay, section 1. Think about it. Before we can do any science, we all have to agree on how we're going to talk about the world. I mean, can you imagine trying to build, a rocket ship if one person is using inches, another is using centimeters, and a third is just using the length of their foot? It would be total chaos, right? That's exactly why we need a universal language in physics.
And for a long time, science really was that chaotic workshop. You had different systems all over the place. But science is a global thing, right? So in 1960, we finally got our act together and formally established the SI system. But here's the really cool part, the thing I want you to notice. We've shifted how we define these units. It used to be based on physical objects, like there was literally a metal bar in France that was the meter. But now we define them using fundamental constants of nature. Things that never ever change. The meter, for instance, is now tied to the speed of light. This is huge. It means anyone, anywhere in the universe could recreate our exact measurement standards just from the laws of physics. How cool is that?
So this whole language of science is built on just 7 letters, what we call fundamental quantities. You can think of them just like the alphabet. We've got length, mass, time, temperature, the real basics. And literally every other quantity we talk about in physics, I'm talking velocity, force, energy, you name it, is a derived quantity. They're just words that we spell by combining those fundamental letters. That's it. It all boils down to just those 7 building blocks.
All right, so we've got our language down. We know the words. But how do we actually use it to describe the world precisely? Well, that's where measurement comes in. And trust me, getting it right is a skill. So let's move away from the pure theory and head over to the lab bench.
Okay, let's clear this up once and for all. Accuracy versus precision. So many people mix these up, but the difference is absolutely critical. Imagine you're an archer. Accuracy is how close you get to the bullseye. Precision is how tightly your arrows are grouped together. See the difference? You could be super precise with all your arrows clustered in a tiny group, but way off in the corner. That's precise, but not accurate. Or your shots could be all over the place, but their average location is the bullseye. That's kind of accurate, but not precise. In the lab, we're always aiming for both. We want that tight little group right in the center of the target.
Now, to get that kind of precision, you can't just use a regular ruler. You need tools like this, the vernier caliper. I know, it can look a little intimidating at first, but I promise it's just a simple 3-step process. First, you just read the main scale, kind of like a normal ruler. Find the last full mark you can see before the 0 on that bottom sliding part. That's your first number. Step 2, and this is the magic part, you look really closely at that sliding scale and find the one line that lines up perfectly with a line on the scale above it. That's your coincidence. And finally, step 3, you just add that little decimal value to your main reading. That's all there is to it. It's a brilliant way to get an incredibly precise measurement.
But let's be real, no measurement is ever perfect. You're always going to have errors. A systematic error is like having a crooked scope on a rifle. It's going to push every single shot in the same wrong direction. It hurts your accuracy. Random errors, on the other hand, are like little unpredictable gusts of wind. They mess with your precision. The best way to fight those? Take a bunch of readings and average them out. And 2 big ones to watch out for in the lab. Always check for a 0 error. Make sure your instrument reads 0 when it should be 0. And with tools that use a screw, like a screw gauge, you have to watch out for backlash error. It's like a little bit of slack in the threads. Pro tip, always make your final turn in the same direction to keep the threads tight. That'll give you a much more reliable reading.
Now on your exam, you can't just write, "My measurement had some error." Nope, you've got to put a number on it. You have to quantify it. Absolute error is the easy one. It's just the raw difference between what you measured and the true value. But think about it. An error of 1 centimeter is a huge deal if you're measuring your phone, but it's totally insignificant if you're measuring the length of a football field.
That's why relative and percentage error are so important. They put the error into context and tell you how big it is in proportion to what you are actually measuring.
All right, section 3. Let's talk about something that I know trips up so many students: significant figures. Please, please, please don't think of these as just some annoying, arbitrary rules you have to memorize. Think of them as the grammar of science. They're a way of communicating to everyone else exactly how precise your measurement is, how much confidence we should have in your number.
So here's the core idea, the one thing you need to remember. Significant figures, or sig figs as you'll hear, are all the digits in a measurement that you know for sure, plus one final digit that you have to estimate. So let's say you're measuring something with a ruler. You can see for sure it's past 23 millimeters, but it's not quite 24. You might estimate it as 23.5 millimeters. The 2 and the 3 are certain. That 5 is your best guess. So that measurement has 3 significant figures.
Okay, so how do you count them? It's actually pretty simple once you know the rules. Rule 1, any non-zero digit is always significant. Easy. Rule 2, any zero that's captured between two non-zero digits is also significant. Think 507, that zero counts. 3, zeros at the very beginning of a number, never significant. They're just placeholders. Now here's the only tricky one, zeros at the end. They only count if there is a decimal point somewhere in the number. That decimal point is basically you shouting, hey, I measured all the way to this decimal place, so this zero is meaningful.
Now, what happens when you do math with these numbers? Here's the golden rule. Your answer can never be more precise than your least precise measurement. Think of it like a chain. It's only as strong as its weakest link. So for adding and subtracting, you look at the decimal places. Your answer is limited by the number with the fewest decimal places. But for multiplying and dividing, you look at the total number of sig figs. Your answer gets rounded to the least number of total sig figs from your starting numbers.
Okay, moving on to section 4. And this, my friends, is your secret weapon for the exam. Seriously. It's called dimensional analysis, and it is the ultimate sanity check for your work. It's a quick way to make sure your equations even make sense in the first place.
The whole thing is based on one simple, non-negotiable rule called the principle of homogeneity. And all it really says is, you can't add apples and oranges. It's that simple. You can't add a distance to a time. You can't set a velocity equal to an acceleration. Every single term in your equation, anything separated by a plus, a minus, or an equal sign, must have the exact same fundamental dimensions, period.
So let's put it to the test with an equation you all know and love. On the left side, we have displacement, s. What's its dimension? Simple, it's just length, or L. Now, let's look at the right side. The first piece is ut, which is velocity times time. The dimensions of velocity are length per time, L over t. We multiply that by time, t, and look at that, the t's cancel out, leaving us with just L. Beautiful. Now the second piece. We've got acceleration, L over t squared, times time squared, t squared. And again, the t squares cancel out, leaving, you guessed it, L. So we have L equals L plus L. Everything checks out. The equation is dimensionally correct.
But, and this is a big but, you have to know its limitations. Dimensional analysis is powerful, but it's not a magic wand. For instance, it has no idea about dimensionless constants. It can't tell you if there should be a 1/2 or a pi in your formula. It also can't derive equations that have plus or minus signs. And here's a tricky one. It can't tell the difference between two totally different quantities that happen to have the same dimensions, like work and torque. So use it as a check, but know what it can't do.
All right, theory time is over. Let's put these tools to the test. I've got a couple of practice problems here that are exactly the kind of thing you can expect to see on your final exam. So I really want you to grab a piece of paper and a pencil and actually try to solve them. I'll read the problem, you can pause, and then we'll go through the solution together. Ready?
Okay, here's the first one. This is a classic lab-style question that pulls together calculations, sig figs, and error analysis. Go ahead and pause here and give it your best shot. Okay, ready for the solution? First, let's find the density. That's just mass divided by volume, and the volume of a cube is its side length cubed. So we have 50.0 grams divided by 2.00 centimeters cubed. That gives us a density of 6.25 grams per centimeter cubed. Simple enough. Now for the error. This is the tricky part. When you multiply or divide quantities, you add their percentage errors, so let's find those. The percentage error in the mass is 0.2 divided by 50.0 times 100. That's 0.4%. The percentage error in the length is 0.01 divided by 2.00 times 100. That's 0.5%. But, and here's the key,
Since we cubed the length in our formula, we have to multiply its percentage error by 3. So the total error is the 0.4% from the mass plus 3 times the 0.5% from the length. That gives us 0.4% plus 1.5% for a final total error of 1.9%.
Okay, problem number 2. This one's a quick one. Let's use our new secret weapon, dimensional analysis, to check this classic formula for the period of a pendulum. Is it dimensionally correct? Pause here and check it out.
And this is just a beautiful example of how elegant this tool is. The left-hand side, t for period, obviously has the dimension of time, t. Now for the right-hand side, first thing, ignore the 2 pi. It's a dimensionless constant. So we're looking at the square root of length, L, divided by acceleration, which is L over t squared. Look what happens. The L's on the top and bottom cancel right out. We're left with the square root of 1 over t squared. When you flip that fraction, it just becomes the square root of t squared. And what's the square root of t squared? It's just t. So we get t equals t. The dimensions match perfectly. The formula solid.
And that wraps up our review session. So I'll just leave you with this one last thought for your exam. We saw how dimensional analysis can confirm the structure of an equation, its skeleton, but it can't tell us the constants. To find those, we need to do careful, precise experiments. And what does that really tell us? It tells us that mathematical theory and physical experiment aren't two different subjects. They're partners. They work together to help us figure out how the universe works. You guys now have the tools for both sides of that partnership. So study well, be confident in what you know, and go ace that exam. You've totally got this.